Hello, ladies and gentlemen. Welcome to, yes, hold your applause, the last lecture of the semester. And it's all about ethers, finishing up chapter 11. And here we go. On this page, there's actually going to be nothing new. It's just reminding us that we already learned how to make ethers with a couple of reactions. And I will just illustrate with examples. If we had a nice secondary carbon with a leaving group, secondary RX, and we react it with an alkoxide. Alkoxide is the general family. That's what this is. This specific one here, this specific one here is isobutoxide. I'll put its name above it. It's a strong nu. To make sure this goes the way I want it to go, I'm going to make sure I use a polar aprotic solvent, such as acetonitrile, polar aprotic, and our analysis from chapter 9 says Mabarf, I don't know, SN2 and SN2. We're going to do an SN2, and then we're going to marvel at how somebody actually put their name on this. Their name is Williamson. Backside attack, leaving group leaves. Stereochemical consequence. H gets pushed out front. Nucleophile came in from the back. We called that backside attack. And we have 2 isobutoxy. That's one of our new groups, right? Isobutoxy pentane as our ether. And the stereochemistry started out R. Yeah, let's do stereochemistry in pink. Started out R and ended as S. Why? Because we did a backside attack. So that method of making ethers has a name, Williamson ether synthesis. I will not test you on the name, but mechanism is good. And knowing the pieces that had to be assembled to make this happen is also good. Acid-catalyzed addition of alcohols to alkenes is this exact same reaction as the acid-catalyzed addition of water to alkenes, except the results in ether instead of an alcohol. So here we just have good old alkene. This time we'll use isobutanol, which I'd like to point out is the conjugate acid of this species up here. That's not related to this question, but just a fact. Catalyst here, sulfuric acid or HOTS. Those two are interchangeable at all times. And the result, without doing the mechanism, does involve a carbocation. As you would guess, with a potential tertiary carbocation, does involve attacking it and generating an oxonium. We did all of this on our first mechanism test. That was test 3. And we have this. This is isobutyl tert hexyl 1, 2, 3, 4, 5, 6 ether. H before I though. Tert hexyl This is its common name. Need a Y there. Tert-hexyl isobutyl ether. It is 3 words. You could have also called it isobutoxy and methyl pentane, both on position 2. And the mechanism, we can do a quick review mechanism, doesn't hurt. Carbocation of the major variety right here. I didn't indicate the minor products, so you don't have to worry about it right now. We made a carbocation there. And isobutanol comes in on the scene. Don't even ask me what happened there. We got that line on the next page. Okay, isobutanol right here. Lone pair, attacks carbocation, generating an oxonium ion. It's got to be our 30th oxonium ion this semester. That might be an understatement. And oxonium ions could be neutralized. We just generated it. Neutralized by the conjugate base of sulfuric acid, which was made in step 1. Neutralizing acid-based stuff. We've done at least 50 of those this semester. Not an overestimate, trust me. Ether. Beautiful. This is a new one down here, condensation of alcohols. Please keep in mind, condensation reactions begin becoming important in Orgo 1, which is this course, near the end. But on every test of Orgo 2, condensation reactions play a prime role. Very important. So remember, condensation is bringing together 2 molecules to make a larger molecule. And during this process, a small molecule, such as water, is lost. Do not confuse condensation with dehydration. Dehydration does not involve 2 molecules coming together. Dehydration is a molecule losing water. There is a relationship. One step in the condensation process will be called a dehydration. That's where the similarity ends. So condensation of alcohols, we'll do 2 different alcohols. We can do something like tert-butanol and butanol coming together with our same favorite acid-catalyzed partners. Anytime you see acid-catalyzed in this course, it's always the same acids that are possible. H2SO4 or HOTS. So acid-catalyzed in this course, it's like a trigger in your head with a hint that says sulfuric acid or toluene sulfonic acid have to be used. We haven't been using HOTS a lot on the notes lately, so let's use HOTS this time. And of course, you're going to generate water. And I just decided now I'm going to make my alcohols have different colors if I'm allowed. Might not be allowed. Just to show you where the water came from, and it's something we can also think about. We had butanol there before. Butanol, its oxygen will end up in the ether for reasons that will be explained during the mechanism. And the water has this color pattern for this specific example. The OH came from the tert-butanol, and the H came from the 1-butanol. So all of the atoms over here are accounted for over here. Two molecules make a bigger molecule while losing water, condensation. The question you always have with a strong acid in the presence of alcohols is, which one should I protonate first? And the guidance towards your answer should be led by the principle of which one would make a better carbocation. And I'm going to protonate the tertiary alcohol because when the water leaves, I'm going to protonate it, it will become an oxonium. And when the water leaves, it will leave behind a tertiary carbocation. So here comes. I would rather protonate tertiary ahead of primary, which is the green alcohol, because it will generate a more stable leaving group, which is another way of saying it will form a carbocation faster. Oxonium is a good leaving group, period. Anytime you can generate an oxonium, you have generated a good leaving group. If you want to be more specific, it's an excellent leaving group. Conjugate base of hydronium, strong acid. Carbocation. Tertiary carbocations are relatively stable, not that hard to make. I bet you could guess, even if you haven't done this mechanism. The two steps we need to get to that ether. We haven't used the green alcohol yet. I'll redraw it here so I don't have to cross mechanism arrows. Lone pair. And we're past the stage where we have that stop at the charge. We have it go all the way to the carbon every time, don't we? And we have our oxonium, number 31. Minimum. What took our oxonium H off last time? Right here. The conjugate base of the acid you started with. Well, here's the acid I started with. Here's its conjugate base generated way back in step 1. TSO minus, tosylate paratoluene sulfonate. Comes in. Whoa, that was a little assertive. Let's do one of these. There. Stops at the H. And you got your catalyst back. HOTS happens, and you get your ether. So lots of ways of making ethers. That's the whole page is synthesis of ethers. 3 main methods, 2 from the past, 1 new. And next up, next up's that crazy blank line. We don't need that page. Synthesis of epoxides. Now remember, epoxides are named after alkenes. That was nomenclature. That is because they are made from alkenes. So in terms of cultural significance, we have a certain culture that when they want to name somebody as the son of somebody, they'll put a Mc in front, like McDonald's means son of Donald. Maybe you didn't know that. Some of you would know that Bin Hussein would be son of Hussein. That's a similar kind of thing. Yeah, you're named after where you came from. Same story here. So if I want to make this epoxide right here, its name is 1-pentene oxide. And where did it come from? The name says where it came from, 1-pentene. And we're going to learn 2 ways of making epoxides. One involves review reactions only. We'll start with that one. And another one involves a new reaction and a very short mechanism. That's welcome news. All right, so review reactions. First, we're going to hit this with water and bromine. So a halogen in water. We call that bromine water. And what you get here is the more electronegative oxygen on the more substituted carbon, and the less electronegative bromine. I apologize. I totally switched my color scheme, right? The alkenes were black, and now the carbons ended up blue, and my halogen ended up black. I think you can see through it. It's been a long semester, right? Okay. Do you remember how we do this mechanism? It's the old Chapter 6 flashback, halohydrin formation. Chapter 6, halohydrin formation. That's what that is. Formation. There's a short form for formation. Okay. Looks like a divide by sign there, doesn't it? Okay. You got to remember bromine first reacts with water. They're sitting there on the shelf. They reacted many years ago, depending on when you made the solution. And they combine thusly. Water does a backside attack on one of the halogens. And you get this bromine attached to hydronium. Bromine with a leaving group, if you think about it. And bromide. Bromide's not going to do anything else today. The important thing is you got a bromine here with a leaving group on it. And bromine's attached to a more electronegative atom. That means bromine's the real positive partner in this, despite what formal charges would hint at. The oxygen, as usual, gets its lone pair to be neutralized. And bromine with its lone pair goes right through the name here to the more substituted carbon, generating a cyclic bromonium intermediate. So step 1 was here. Step 2 is here. We generated a cyclic bromonium. Now popping that open goes by the rules of carbocation stability. You see this cation here? There's a cation in this intermediate. That's a big hint. If there's a cation in the intermediate, then opening up the triangle is going to go to the carbon that spends more time with the positive charge. I've said that a few times, I am very sure. And water is everywhere. And it comes and attacks the more substituted carbon. And you generate an oxonium ion. And it looks like I drew the flip of the molecule on the top of the screen. Had the water coming in from underneath. Bromine on the other side. Remember, backside attack on a triangle. Anti-stereoselectivity. Although it's a freely rotating molecule, it doesn't really matter. At this instant, they'd be syn. In the end, they're anti. Oh, sorry. Here they're anti. In the end, they might be syn after rotation. A lot of talk about nothing. Don't worry about it. How do I neutralize that oxonium? That's a good question. The best base available and the most prevalent base available is water. H2O. I don't know where to put it without being too confusing. Water's everywhere. Just like Mr. Coleridge says. Water, water everywhere. Not a drop to drink. And then we have this becoming our vicinal halohydrin. Vicinal because they're on adjacent carbons. All I'm going to treat that vicinal halohydrin with is hydroxide. KOH, a good example. So this was step 1. We did the mechanism for step 1 down here. And 2 is right here. We'll do the mech for 2 up here. What we have is an alcohol. And we have hydroxide. Hydroxide's a base. Bases deprotonate alcohols. KEQ is close to 1. You can make sure you get a good yield of that just by using a large excess of hydroxide. Don't even worry about that. It's not a lab course. Don't have to worry about yields here. Acid base happens in lecture course. Now I've generated a molecule that's got a strong nu at the same time that it has an LG. Oh, LG. What letters are coming to mind? I hope those letters are NGP. Except this time it's like just the first step of NGP. Backside attack inside the same molecule, leaving group leaves, and you made your epoxide. I wonder if I can move its name a little. There we go. You made 1-pentene oxide. And before break, think we don't have a lot of time. We don't need a lot of time. This is another method. This is a new one. We're going to use a per acid. Pen just took a break. Per acid of this variety. Per acid epoxidation. Here is a simple per acid. And it's a carboxylic acid with an extra oxygen. Are you surprised its name is per acetic acid? Normal acetic acid's missing one of these O's. Per acetic acid has the extra O. Those two are going to react. And you're going to make the same epoxide you made above. Just a little hint here, that's a red O. And side product, not that we're that concerned about side products. And I'm drawing it this way for a reason to try to help guide us through the mechanism. I have the alcohol on top, not the alcohol, the hydroxy portion of the carboxylic acids on top here. And it used to be the carbonyl. The proton used to be here. It ended up there. This O is gone. This is the O. That one. No other O ends up here. I'm going to put a little green dot in the middle of it. It has to be that O. And the only reason it has to be that O is the mechanism goes like this. I'm going to go with light pink mechanism. Pi attacks O. We do that because O has an adjacent O, and that makes it suffer from lone pair repulsions. So normally you don't see O attacked, right? But when there's lone pair repulsions, we saw during the hydroboration oxidation reaction, an atom move over to an O bonded to an O. So it took its electrons to an O. And we're seeing something similar here. And we're resonating. There's the carbonyl. As promised, there's the carbonyl on the bottom. Old carbonyl goes here, picks up a proton, and now that would be a second bond to H. The question that remains is, what do you do with this pair of electrons? Well, this pair of electrons, if it is left without any additional arrows, would generate a carbocation on one of the carbons, and I think you know which one's the better one. It's this one. This pair of electrons comes back to the more substituted carbon. Have I ever said that sentence before? I think about 15 times this semester. I've said, bring the pair of electrons back to the more substituted carbon. And the nice news about this mechanism is it's over. It's done. It's arrows only, this mechanism. And no intermediates. You go straight to the epoxide, the 1-pentene oxide, and the side product, acetic acid. Its name lost the per. Because it lost its extra oxygen. And that's all that needs to be said about this reaction. And that's a good spot to leave for our first break. Coming up will be our discussion of a blank page, followed by a discussion of reactions of ethers with hydrochloric, hydrobromic, or hydroiodic acids, and then acid-catalyzed hydrolysis of ethers, which will be a very similar process. And I will leave you till then and see you very shortly. Ooh.